The date burned itself into aviation history. August 14, 1943. The clock showed 1847 hours. At 28,000 feet above the Solomon Sea, something was about to change everything. Captain Robert Dutch Kellerman gripped the controls of his P-38 Lightning. The aircraft sliced through tropical air. Speed held steady at 420 miles per hour. Twin Allison engines thundered in perfect harmony. The sound filled his cockpit like rolling thunder. Below his wings, 3 Japanese Zero fighters tumbled toward the ocean. Black smoke trailed behind them. They looked like funeral ribbons against the blue water. But Kellerman felt no victory. His instrument panel told a different story. Manifold pressure gauges climbed higher. Red zones appeared on both engines. The needles moved into dangerous territory. Heat built up inside the engine compartments. Both power plants ran far too hot. Time was running out fast. Maybe 60 seconds remained. Perhaps 90 at most. Then the superchargers would fail completely. He would become the 4th kill of the day. Only this time, he would be the enemy's victory. What Kellerman could not know changed everything. 8,000 miles away, a solution was taking shape. In Burbank, California, a breakthrough was happening. A 34-year-old engineer named Howard Ainsworth had just cracked the code. He had solved what military brass called physically impossible. The solution would transform the P-38 completely. A promising but troubled fighter would become something else entirely. German pilots would learn to fear it. They would call it the Gabelschwanz-Teufel, the fork-tailed devil. Japanese pilots had their own name ready. After Ainsworth's modification reached the Pacific theater, they would whisper it in fear. They called it Sure no Kaga, the shadow of death. What followed was more than engineering brilliance. It was a complete reversal of everything. Tactical doctrine would shift overnight. Air superiority would change hands in both theaters. Sometimes victory and defeat balance on a knife's edge. Sometimes one man refusing to accept impossible makes all the difference. The problem had haunted the P-38 since its first combat deployment. November 1942 marked the beginning of a nightmare. Lockheed's engineers had created something revolutionary on paper. Twin engines, twin booms, tricycle landing gear, a central nacelle housing pilot, and armament. The specifications promised American air superiority everywhere. The XP-38 prototype had made history on January 27, 1939. Lieutenant Benjamin Kelsey took the controls that day. The test flight launched from Marchfield, California. The aircraft demonstrated speeds exceeding 400 miles per hour. It became one of the fastest aircraft in the world overnight. Army Air Corps procurement officers saw the future. They immediately ordered 13 evaluation aircraft. The designation read YP-38. Everyone believed they had a war winner. But combat tells different stories than test flights. By late 1942, reports painted a devastating picture. The AAF's first fighter group operated P-38Fs from North African bases. Mission-critical failures occurred with terrifying frequency. Between November 1942 and February 1943, mechanical failures claimed 23 aircraft. Enemy action killed fewer pilots than their own engines. The mechanical casualties stemmed from one catastrophic flaw. Engineers at Lockheed's Burbank facility had missed it completely. Peacetime testing never revealed the problem. At high altitudes, specifically above 25,000 feet, strategic bombing escorts operated in death zones. The P-38's Allison V-17-10 engines experienced violent power fluctuations. Pilots called them the rattles. Technical documentation from Wright Field's Engineering Division laid out the failure mechanism in cold detail. The P-38's twin-turbo superchargers were designed to maintain engine performance at altitude. They compressed thin air before it entered the cylinders. But they were experiencing backfire events instead. These backfires sent pressure waves backward through the induction system. The engines would stumble, power would vanish. In extreme cases, complete failure followed. The mathematics were straightforward. The solution seemed impossible. At 28,000 feet, atmospheric pressure drops dramatically. It falls to approximately 4.3 pounds per square inch. Sea level pressure measures 14.7 psi. The turbo superchargers had to compress this thin air. They needed to maintain manifold pressure around 52 inches of mercury. Combat power settings demanded this performance. The backfire phenomenon occurred when compressed air-fuel mixture ignited prematurely. Instead of burning in the engine cylinders, it exploded in the supercharger ducting. The resulting pressure spike traveled backward at supersonic speeds. It reached the carburetor in milliseconds. This reverse pressure wave disrupted fuel metering completely. It created lean mixture conditions. Additional backfires followed in cascading failure cycles. Lieutenant Colonel Cass Hu led the 14th Fighter Group's P-38 operations from England. He documented the tactical consequences in after-action reports. The date showed January 1943. His words were stark and unforgiving. Enemy fighters exploit our power loss by engaging above 25,000 feet. Our pilots face impossible choices. They can maintain altitude with unreliable engines, or they can descend to where engines work but enemy advantage increases. Either choice results in unacceptable casualties. The Pacific Theater faced identical problems. Major General George Kenney commanded 5th Air Force operations. He had received P-38s specifically to counter Japanese fighters. These enemy aircraft operated at high altitudes over New Guinea. His March to 1943 communication to Army Air Forces headquarters was brutally direct. The P-38 at altitude is a liability, not an asset. Until engine reliability matches performance specifications, I cannot recommend this aircraft for strategic operations. Lockheed's response was immediate. Engineering teams deployed to forward bases in both theaters. These field investigations lasted from December 1942 through March 1943. They confirmed what pilots already knew with deadly certainty. The problem was real. It was consistent. It was killing people. Engineers documented backfire events in 73% of high-altitude combat sorties. These missions lasted more than 45 minutes. The corporate implications were staggering beyond belief. Lockheed held production contracts for 2,100 P-38 aircraft. The contracts represented $270 million in military procurement. The Army Air Forces had planned their entire twin-engine fighter doctrine around P-38 capabilities. If the altitude problem could not be solved, the entire program faced cancellation. Wright Field's Propulsion Division assigned 17 engineers to develop solutions. Between January and May 1943, they tested 23 different modifications. They revised carburetor jets. They modified supercharger waste gate controls. They adjusted ignition timing. They tried different fuel mixtures. Various induction system redesigns followed. Every modification either failed to solve the problem or created new complications. By June 1943, Wright Field's position was crystal clear. The Chief of Fighter Development issued an unambiguous statement. The backfire phenomenon in twin turbo-supercharged installations at combat altitudes represents a fundamental limitation of current technology. No practical field modification can eliminate this condition without complete engine redesign. The word impossible appeared in official correspondence 47 times. Various technical reports and recommendations dated between March and July 1943 all said the same thing. It could not be fixed. Howard Ainsworth read those reports with particular skepticism. He was a senior propulsion engineer at Lockheed's Burbank facility. Problem solvers who refuse to accept conventional limitations think differently. They see possibilities where others see walls. Howard Ainsworth had joined Lockheed Aircraft Corporation in 1937. He arrived 6 months before the XP-38 prototype's first design review. His background was unconventional for aerospace engineering. A mechanical engineering degree from Purdue University came first. Then 3 years designing industrial compressor systems for Chicago Pneumatic Tool Company followed. That compressor experience would prove decisive. While other engineers approached the P-38's backfire problem from an aviation perspective, Ainsworth saw something different. He recognized it as fundamentally an industrial gas flow problem. It just happened to occur in an aircraft engine. The breakthrough came on June 19, 1943. Building 304 at Lockheed's Burbank facility witnessed history. Ainsworth had spent 3 weeks analyzing high-speed pressure recordings from test engines. He looked for patterns that others had missed. The data showed something unexpected and crucial. Backfires did not occur randomly. They followed a specific pressure oscillation pattern. This pattern began 0.3 seconds before the actual backfire event occurred. This pre-backfire pressure wave was the signature Ainsworth had been searching for. In industrial compressor systems, he had seen similar oscillations. They preceded surge events. These were catastrophic flow reversals that could destroy equipment completely. The solution in industrial applications used an anti-surge valve. It bled off excess pressure before oscillations could build to destructive levels. Could the same principle work in an aircraft engine induction system? The concept seemed elegantly simple. Install a pressure relief valve in the supercharger discharge ducting. Program it to open automatically when pressure oscillations began. Bleed excess compressed air overboard before backfire conditions could develop. The valve would need lightning-fast response times. It had to respond in milliseconds. It must operate reliably at extreme altitudes and temperatures. Weight was critical in an aircraft already struggling with power-to-weight ratios. Ainsworth's initial calculations suggested hope. A valve assembly weighing approximately 2.3 pounds per engine could prevent backfire events. It would release less than 5% of compressed airflow during oscillation conditions. This minor air loss would cause negligible power reduction. Compare that to the catastrophic power loss from backfires. The trade-off was obvious and compelling. The challenges were formidable and complex. The valve needed to distinguish between normal pressure fluctuations and pre-backfire oscillations. It had to operate at temperatures ranging from minus 60 degrees Fahrenheit at altitude to plus 300 degrees in engine compartments. It must function in atmospheric pressures as low as 4 psi. It required no pilot input or electrical power. Ainsworth's design used a purely mechanical system, a spring-loaded poppet valve connected to a pressure-sensing diaphragm. The system was tuned to respond specifically to the frequency and amplitude of pre-backfire oscillations. When the diaphragm detected the characteristic pressure wave, it would overcome spring tension. The valve would crack open for approximately 0.8 seconds, just long enough to disrupt the oscillation before backfire occurred. On July 2, 1943, Ainsworth presented his proposal to Lockheed's chief engineer, Hall Hibbard. The presentation lasted 17 minutes. Hibbard's response was immediate and decisive. Build a prototype. You have 2 weeks and whatever resources you need. The fabrication took 11 days. Lockheed's machine shop produced the valve bodies from aluminum alloy. Spring and diaphragm assemblies came from specialized suppliers. These suppliers were told only that parts were for critical war production. Security protocols prohibited explaining the actual application. The first bench test on July 13, 1943, showed genuine promise. Using a test rig that simulated high-altitude supercharger conditions, Ainsworth's valve responded correctly. It reacted to induced pressure oscillations perfectly. Opening and closing occurred in precise timing exactly as calculations had predicted. But bench tests were not combat conditions. The real validation would require flight testing under actual high-altitude combat power settings. These were exactly the conditions where P-38s had been failing with fatal consistency. On July 21, 1943, a P-38 G-10 rolled onto the test ramp at Lockheed's Burbank Airfield. Serial number 4213559 would make history. Maintenance crews had installed Ainsworth's prototype valves on both engines overnight. The valve assemblies were barely visible. Small cylindrical units tucked into the supercharger ducting. They connected to discharge manifolds by half-inch aluminum tubes. Lockheed test pilot James Milo Burcham completed pre-flight inspection at 0545 hours. His test card specified a profile that had destroyed engines on previous attempts. Climb to 30,000 feet. Establish combat power settings of 52 inches manifold pressure and 3,000 revolutions per minute. Maintain those settings for 45 minutes while executing combat maneuvers. At 0612 hours, Burcham advanced the throttles. The P-38 accelerated down runway 07. Twin Allisons reached takeoff power. 1325 horsepower per engine thundered to life. The fighter lifted off after a ground roll of 1,450 feet. The climb to test altitude took 19 minutes. Burcham's voice, recorded on the flight test data recorder, remained steady as he reported progress. Passing through 25,000 feet. The altitude, where previous tests had begun, experiencing problems. 28,000 feet, leveling off. Manifold pressure 52 inches both engines. RPM 3000. Oil temperatures normal. Cylinder head temperatures normal. Initiating combat maneuver sequence. For the next 47 minutes, Burcham threw the P-38 through every combat maneuver in the tactical playbook. Maximum rate turns stressed the airframe. Chandelles tested climb performance. Split S reversals pushed structural limits. High G pullouts challenged both pilot and machine. Sustained climbs at combat power demanded everything from the engines. Flight test engineers monitoring from the ground listened to engine parameters that remained rock-solid stable. No backfires interrupted the smooth power delivery. No power fluctuations disrupted performance. No rattles shook the aircraft. The engines ran like they had been designed to run all along. At 07:18 hours, Burcham keyed his radio with words that would change aviation history. Test complete. Engines performed flawlessly throughout the entire profile. Whatever Ainsworth built, it works perfectly. The data recorders told the complete story in precise detail. During the 47-minute test at altitude, the pressure relief valves had activated 23 times. Each activation lasted between 0.6 and 1.1 seconds. Every single activation had occurred precisely when pressure oscillations began building toward backfire conditions. The valves had prevented backfires before they could develop, exactly as Ainsworth's theory had predicted. The successful test flight on July 21st triggered immediate mobilization at Lockheed's Burbank facility. Hall Hibbard convened an emergency meeting at 1400 hours that same day. Production managers attended. Engineering leads gathered. Military liaison officers from Wright Field participated. The question was not whether to implement Ainsworth's modification. The test data made that decision obvious and urgent. The question was speed. How quickly could Lockheed retrofit existing aircraft and incorporate the modification into production models while maintaining delivery schedules for 67 new P-38s per month? Captain Theodore Vickers represented the Army Air Force's Material Command. He brought sobering context to the meeting that afternoon. Combat loss reports from the previous 30 days painted a grim picture. 31 P-38s lost to engine failures in the European theater. 18 more lost in the Pacific. Each loss represented not just an aircraft worth $120,000. An irreplaceable pilot who required months of training was gone forever. "Gentlemen," Vickers stated, reading from classified casualty reports, "we are losing P-38s to mechanical failure at nearly the same rate we are losing them to enemy action. Every week, this modification is not in the field costs lives and aircraft we cannot afford to lose." Production manager Raymond Couture outlined the manufacturing challenge ahead. Each valve assembly required precision machining of 7 separate components. Specialized spring tempering was essential. Careful calibration of the pressure-sensing diaphragm demanded expertise. Current machine shop capacity could produce approximately 40 valve sets per week. That was enough for 20 aircraft. At that production rate, retrofitting the 423 P-38s currently in operational service would take 21 weeks. Meanwhile, pilots would continue dying in aircraft with unfixed engines. Ainsworth proposed a solution that violated every conventional production protocol. Rather than waiting for full engineering documentation and formal military approval, Lockheed could begin producing valve assemblies immediately. They would base production on prototype specifications. Technical documentation could be developed in parallel with manufacturing. The risk was substantial and real. If subsequent testing revealed problems requiring design changes, Lockheed might have to scrap hundreds of already manufactured valve assemblies. The financial exposure could exceed $200,000. That was serious money in 1943. Hibbard made the decision in less than 5 minutes. "Start production immediately. I will take responsibility for any costs if we have to redesign. These valves are saving pilot lives right now in test flights. We are not going to delay that benefit by waiting for paperwork." By July 23, 1943, just 2 days after the successful test flight, everything changed at Lockheed's machine shops. Production priorities were reorganized completely. 3 complete machining cells were reassigned exclusively to valve component production. The company contacted 14 specialized suppliers. They needed spring assemblies, diaphragm materials, and aluminum stock in unprecedented quantities. The production scale-up revealed Ainsworth's genius for practical engineering solutions. His design used almost entirely standard aircraft materials and components. The valve bodies could be machined on equipment already producing P-38 parts. The springs used standard music wire available from existing suppliers. Even the pressure-sensing diaphragms used material already specified for other aircraft systems. This design philosophy made all the difference. Using standard materials in novel configurations, rather than requiring exotic new components, allowed production to accelerate far faster than anyone had anticipated. By August 1st, production had reached 73 valve sets per week. By August 15th, production hit 127 sets per week. The numbers kept climbing. Parallel to production ramp-up, Lockheed initiated an aggressive testing program. The modification needed validation across the full P-38 performance envelope. Between July 23 and August 20th, test pilots flew 147 test sorties. They accumulated 412 hours at high altitude under combat power settings. Every hour validated Ainsworth's breakthrough. The testing revealed only minor refinements needed. Spring tensions required slight adjustments to account for temperature variations. Desert and Arctic operating environments created different demands. The valve mounting brackets needed reinforcement to handle vibration loads during sustained combat maneuvering. These changes were incorporated into production within days of discovery. More importantly, the testing revealed an unexpected benefit that no one had anticipated. Pilots reported that engine responsiveness had improved across all altitude ranges. Not just at high altitude where the problem was most severe. The pressure relief valves were apparently smoothing out minor pressure fluctuations. These had been creating subtle power irregularities throughout the engine's operating range. Test pilot Joseph Foltz documented this discovery in his flight report from August 8th. Throttle response is noticeably crisper. Power changes are immediate and smooth. The engines feel more willing, like they have been waiting to perform this way all along. The military approval process typically consumed months. Bureaucratic marathon required committee reviews and formal testing at Wright Field. But this time was compressed to unprecedented speed. Captain Vickers recognized the combat urgency. He personally carried Ainsworth's technical documentation and test data to Wright Field on August 4th. The Wright Field engineering review took 6 days. A process that normally required 6 weeks was completed in less than 1 week. On August 10th, the Army Air Force issued Technical Order 01-25AN-43. This document officially authorized installation of the Ainsworth pressure relief valve modification on all P-38 aircraft. The retrofit program began immediately. Lockheed established modification centers at 3 strategic locations. The Burbank factory would handle West Coast units. A facility at Patterson Field, Ohio, would process European-bound aircraft. A forward modification center at Eagle Farm Airfield in Brisbane, Australia, would serve Pacific Theater operations. Each location had the expertise and equipment needed. The modification procedure required approximately 16 man-hours per aircraft. Mechanics had to access the supercharger ducting carefully. Install the valve assemblies precisely. Connect the pressure sensing lines correctly. Perform ground runs to verify proper operation. It was delicate work requiring precision and skill, but it was work that could be done in field conditions. Aircraft did not need to return to depot-level maintenance facilities. Before we continue this incredible story, tell us where you are listening from today. If this engineering triumph inspires you, make sure you hit that subscribe button. Tomorrow brings something extraordinary that you will not want to miss. September 3, 1943, 06:23 hours marked a new chapter in aviation history. Dobodura Airfield in New Guinea witnessed the first combat test of everything Ainsworth had created. Captain Gerald "Red" Hutchins performed his pre-flight walk-around on P-38 G-15, serial number 432204. This was the first combat aircraft in the 5th Air Force to receive Ainsworth's modification. The installation had been completed just 18 hours earlier. A traveling Lockheed technical team had flown 7,200 miles from Burbank specifically to retrofit forward deployed fighters. Hutchins commanded the 39th Fighter Squadron's Flying Cobras. His unit had lost 4 aircraft to engine failures in the previous 6 weeks alone. His mission briefing that morning called for high-altitude escort of B-24 Liberators. The target was Japanese shipping at Wewak Harbor. This was exactly the type of operation where P-38s had been experiencing catastrophic engine problems. The mission profile demanded everything the P-38 had struggled to deliver consistently. Climb to 27,000 feet. Maintain formation for 340 miles. Engage enemy fighters at altitude if necessary. Return to base safely. Total flight time would be approximately 4 hours at combat power settings. Every minute would test Ainsworth's engineering breakthrough. At 06:44 hours, Hutchins advanced throttles and felt the familiar surge. 2,600 combined horsepower pulled the fighter down Dobodura's coral runway. The P-38 lifted off and began the long climb toward rendezvous altitude. 23 minutes later, passing through 26,000 feet, Hutchins instinctively tensed. This was the altitude where engines typically began their deadly misbehavior. His eyes scanned the instrument panel with practiced urgency. Manifold pressure held steady at 50 inches. Cylinder head temperatures showed normal. Oil pressure remained solid and unwavering. No fluctuations threatened performance. No power loss interrupted smooth operation. The engines ran with a smoothness he had never experienced at this altitude. The bomber escort mission proceeded without any mechanical incident whatsoever. At 08:47 hours, radar controllers vectored Hutchins's flight toward incoming enemy aircraft. 6 Nakajima Ki-43 Oscar fighters were attempting to intercept the B-24 formation. What followed demonstrated not just reliability, but the tactical advantage that reliability enabled for the first time. Hutchins's after-action report, filed at 13:20 hours that afternoon, described the engagement with professional precision. Engaged 6 enemy aircraft at 26,500 feet. Engine performance remained flawless throughout combat maneuvering. Sustained combat power for 11 minutes without any power fluctuation. Destroyed 1 enemy aircraft confirmed. 1 probable. All bombers returned safely to base. The significance transcended a single successful mission by far. For the first time, P-38 pilots could fight at high altitude with complete confidence in their engines. The psychological impact was as important as the mechanical reliability. Pilots who had been holding back, conserving power, managing engines instead of fighting enemies, could now engage with full commitment. The tactical implications were transformative and immediate. Within 2 weeks, 31 P-38s in 5th Air Force had received the modification. Mission reports documented a fundamental shift in combat effectiveness that changed everything. Between September 3 and September 17th, modified P-38s flew 247 combat sorties at altitudes above 25,000 feet. Not a single aircraft was lost to engine failure. The curse had been broken forever. Not a single engine quit working. The enemy lost aircraft. 19 confirmed kills. 7 more probably destroyed. Major General George Kenney had written harsh words about P-38 dependability just months before. Now he grabbed his radio on September 19th. His priority message shot straight to Army Air Force's headquarters. The modified P-38 is a completely different machine. Engine dependability at high altitude now surpasses single-engine fighters. Speed-up modifications for every P-38 in theater. Pacific combat trials gave us information no laboratory could ever provide. Those new valves worked perfectly. Tropical humidity hung thick at 95%. Ground temperatures scorched at 110 degrees. Up high, the air froze at -50. Violent combat maneuvers stressed every component. Everything held together beautifully. Japanese intelligence was listening. They monitored American radio chatter constantly. Something had changed in the tactical patterns. Intercepted Japanese Naval Air Force messages from late September 1943 told the story. Enemy twin-engine fighters showed improved high-altitude performance. Japanese pilots received new warnings. P-38s were no longer sitting ducks above 8,000 meters. The fear that had crept into Japanese pilot voices was unmistakable. Their advantage was disappearing. European theater validation came weeks later. The results proved just as stunning. The 55th Fighter Group operated from Nothamsted in England. Modified P-38s began arriving September 28, 1943. Their mission was brutal beyond description. escort B-17 flying fortresses deep into German territory. Leave those fighters nowhere to hide at altitudes exceeding 28,000 feet. Colonel Frank James commanded the 55th Fighter Group. He had watched 8 aircraft die from engine failures between June and September. His pilots developed dark humor to cope with the terror. The Germans might kill you, but your engines will get you first. Those words echoed through ready rooms like a death sentence. The first major test arrived October 8, 1943, maximum effort mission to Bremen. Every available aircraft launched. 64 P-38s from the 55th and 20th Fighter Groups took off. They would escort 350 B-17s on a round trip lasting nearly 5 hours. Every single P-38 carried those new valves. The mission would encounter resistance like nothing they had seen before. The Luftwaffe threw everything at them. An estimated 140 German fighters rose to meet the bombers. Messerschmitt Bf-109s climbed aggressively. Focke-Wulf FW-190s dove from above. The air battle erupted with savage intensity. Combat raged between 26,000 and 31,000 feet. This was the exact altitude where unmodified P-38s became helpless victims. Now they were predators. Lieutenant Colonel Jack Jenkins led the 55th Fighter Group's 338th Fighter Squadron. His mission report captured the transformation perfectly. We engaged superior numbers of enemy aircraft at extreme altitude. The battle lasted 37 minutes of continuous combat. Engine performance never wavered once. Pilots reported complete confidence in power response during high-G maneuvers. This modification has transformed our combat capability beyond recognition. The mission results spoke with mathematical precision. 11 German fighters destroyed. 4 probably destroyed. 7 damaged beyond repair. Only 2 P-38s lost to combat damage. 0 lost to mechanical failure. Every bomber reached the target. Every bomber returned safely. German fighter pilots had grown accustomed to exploiting P-38 weaknesses. They expected easy victories above 25,000 feet. Instead, they faced aircraft that could outmaneuver them, outclimb them, outfight them at altitudes they had previously dominated. The psychological shock rippled through Luftwaffe squadrons. Captured tactical reports from October 1943 revealed their desperation. They described unexpected American twin-engine fighter aggressiveness at high altitude. New recommendations went out immediately. Avoid engagement above 8,500 meters unless holding numerical superiority of at least 3 to 1. The hunters had become the hunted. By November 1943, combat data from both theaters provided overwhelming statistical proof. Modified P-38s had flown 3,147 combat sorties at high altitude. The mechanical failure rate dropped to 0.3%. This represented a 96% reduction compared to unmodified aircraft. Combat effectiveness told an even more dramatic story. Enemy aircraft destroyed per 100 sorties had increased 340%. The numbers were staggering. The human cost savings struck even deeper. Between August and November 1943, P-38 pilot casualties from mechanical causes plummeted. Deaths dropped from 23 per month to fewer than 2 per month. Each of those lives represented irreplaceable value. Every pilot had survived 6 months of grueling training. Hundreds of flight hours accumulated through countless practice sessions. Combat experience that could never be replaced quickly. These men could continue contributing to the war effort instead of dying in flaming wreckage. Technical intelligence officers discovered an unexpected bonus. The reliability improvement created psychological effects beyond mere confidence. Pilots flying modified P-38s reported dramatically reduced stress levels, lower fatigue during long missions. Knowing their engines would perform reliably freed their minds completely. They could focus entirely on tactics and combat effectiveness. No longer did they constantly monitor engine instruments for signs of impending disaster. Flight surgeon Captain Lawrence Anderson worked with the 55th Fighter Group. His medical reports from November 1943 documented remarkable changes. Pilot stress indicators have decreased measurably since modification implementation. Post-mission physical examinations show reduced blood pressure elevations. Cortisol levels dropped significantly. Pilots are sleeping better. They report improved concentration during combat. The psychological burden of unreliable equipment was greater than we ever realized. The success of those pressure relief valves created shockwaves throughout American aviation. By December 1943, engineering teams across the industry studied the modification intensively. This was not just a fix for one aircraft's problems. This represented a fundamental breakthrough in turbo-supercharger technology. Wright Field's Propulsion Research Division launched a comprehensive study in October 1943. They needed to understand why this relatively simple mechanical solution succeeded. Extensive engineering efforts had failed completely. The study completed in January 1944. Classification level remained restricted throughout the war. The analysis identified three revolutionary factors. First, the engineer had approached the problem from first principles. He refused to accept existing assumptions about turbo-supercharger operation. While others sought to prevent backfires by modifying fuel mixtures, ignition timing, or supercharger control systems, he recognized something different. The fundamental issue was pressure wave dynamics in the induction system. His solution addressed the root cause rather than symptoms. Second, the purely mechanical nature eliminated complexity and failure modes. Other proposed solutions required electrical actuators, pilot-controlled systems with multiple switches, complex linkages that could break under stress. This design operated automatically, required no external power whatsoever, exactly one moving part: the spring-loaded poppet valve itself. Simplicity was genius. Third, and perhaps most significantly, the modification improved performance across the entire operating envelope, not just at high altitude where problems were most obvious. The pressure relief function smoothed power delivery throughout all flight regimes. It damped pressure oscillations that had been creating subtle irregularities, even when they didn't escalate to full backfires. These insights influenced an entire generation of aircraft engine development. The North American P-51 Mustang entered widespread service in 1944. Its Packard-built Merlin engine incorporated pressure relief principles from the beginning. The Republic P-47 Thunderbolt's turbocharger system received similar modifications in late production models. Even more significantly, the valve concept shaped post-war jet engine development. Early turbojet engines experienced compressor surge, a phenomenon remarkably similar to the backfire events that had plagued P-38s. Engineers at General Electric and Pratt and Whitney studied the declassified reports after 1945. They developed anti-surge systems for jet engines based on identical fundamental principles. Detect pressure oscillations before they cascade into catastrophic events. Bleed excess pressure to interrupt the destructive cycle. Dr. Theodore von Karman directed the Army Air Force's Scientific Advisory Group. He cited this modification in a 1946 report on wartime aeronautical innovations. The pressure relief valve represents elegant engineering, solving a complex problem with minimal intervention at precisely the right point in the system. This approach of finding the leverage point matters enormously. Small changes can produce large beneficial effects. This should guide all future development efforts. The modification's success influenced military procurement philosophy permanently. Before this breakthrough, conventional wisdom held firm beliefs. Complex problems required complex solutions developed over extended time periods. Bureaucratic processes moved slowly for good reasons. The rapid development, testing, and fielding of the pressure relief valve shattered those assumptions. From concept to combat validation in just 76 days. Innovative engineering could deliver solutions faster than bureaucratic processes assumed possible. This lesson shaped post-war acquisition strategy completely. It led to establishment of rapid development programs. These would eventually produce aircraft like the F-86 Sabre and F-104 Starfighter. Accelerated timelines compared to pre-war development cycles became the new standard. This philosophy produced remarkable results. The F-86 Sabre went from design start to first flight in just 28 months. The F-104 Starfighter achieved similar timeframes. The institutional memory of how quickly the P-38 modification had transformed combat effectiveness became a benchmark. Aggressive engineering timelines could achieve incredible results when supported properly. Veterans who flew modified P-38s carried memories that shaped their entire post-war lives. Major Richard Bong became America's highest-scoring ace with 40 victories. He credited the modification with saving his life multiple times. His tragic death in a test flight accident in August 1945 robbed the nation of a genuine hero. Charles MacDonald commanded the 475th Fighter Group's top squadron. After the war, he became a commercial airline pilot. He insisted his airline's maintenance standards matched the reliability he had experienced in modified P-38s. No compromise was acceptable. The aircraft themselves became living monuments. Those few that survived scrapping became museum pieces and warbird restorations. They preserved tangible evidence of the modification's impact for future generations. The Smithsonian's National Air and Space Museum acquired P-38J-10LO, number 426762. This aircraft carried those special valves throughout 84 combat missions in Europe. The placard beside the restored aircraft specifically mentions the modification. It identifies the engineering breakthrough that transformed the P-38 from problematic to dominant. Annual reunions of P-38 pilot associations continued from 1946 until the last gathering in 2019. These events consistently featured discussions of the modification's impact. Veterans who had flown both modified and unmodified aircraft spoke of before and after as distinct eras in their combat experience. The transformation was that complete. Colonel Jack Jenkins led the 55th Fighter Group through fierce air battles over Germany. At the 1987 reunion, he made a statement that captured everything perfectly. We talk about the battles we won, the missions we flew, the friends we lost. But we don't talk enough about the engineer whose work let us win those battles. Let us survive those missions. That engineer saved more P-38 pilots than enemy fighters killed. That's his real legacy. The engineer himself remained characteristically modest about his contribution until his death in 1979 at age 70. His obituary in Aviation Week mentioned the P-38 modification in just 2 sentences. His family reported he considered it simply doing the job I was hired to do. During a time when good work mattered more than recognition. Yet recognition came nonetheless over the years. In 1983, the American Society of Mechanical Engineers designated the pressure relief valve modification as a historic mechanical engineering landmark. They acknowledged its profound impact on aircraft engine reliability and combat effectiveness during World War II. The bronze plaque installed at Lockheed's Burbank facility noted something important. The engineer's elegant solution to a complex problem exemplified engineering excellence in service of urgent national need. The Society of Automotive Engineers inducted the engineer posthumously into their Hall of Fame in 1991. They cited the modification as demonstrating how fundamental engineering principles creatively applied can solve problems. Problems that appear intractable when approached conventionally suddenly become manageable. Modern aviation engineering students study this approach as a case study in problem-solving methodology. MIT's aeronautical engineering program includes the P-38 modification in coursework on first principles engineering. They use it to illustrate how questioning assumptions matters. Returning to fundamental physics can reveal solutions that incremental improvements miss completely. The modification's principles continue influencing current technology. Modern turbofan jet engines incorporate multiple pressure relief systems descended from the original concept. The bleed valves that prevent compressor surge in contemporary aircraft engines operate on identical fundamental principles. Detect pressure instabilities and relieve them before they cascade into failures. The complete story defies simple categorization. It was simultaneously an engineering triumph and a life-saving intervention, a strategic game-changer, and a demonstration of individual brilliance. How one person can alter historical trajectories when circumstances align with capability. The mathematics of impact are straightforward, but staggering. Approximately 2,847 P-38 aircraft received the modification during wartime service. Statistical analysis suggests the modification prevented roughly 387 aircraft losses to mechanical failure. An estimated 290 pilot lives were saved. Each of those pilots averaged 18 months of subsequent combat service. They contributed to collective totals of thousands of additional combat sorties. Hundreds of enemy aircraft destroyed. Countless bomber crews protected by reliable escort fighters. But numbers alone cannot capture the full dimension of impact. The modification changed what was possible in aerial combat permanently. Before this breakthrough, high-altitude supremacy remained contested. Advantage shifted based on which side could temporarily overcome engine limitations. After the modification, American forces held altitude advantage permanently in both theaters, a strategic asset that influenced every subsequent air operation. The psychological dimension proved equally significant. Japanese and German pilots who had learned to exploit P-38 weaknesses found themselves hunted. They faced an aircraft they could no longer counter effectively. American pilots gained confidence that transformed tactical aggressiveness and mission success rates. Bomber crews pressed attacks more determinedly. They knew reliable escorts could maintain protective coverage throughout entire missions. The strategic bombing campaigns that devastated Axis industrial capacity succeeded partly because P-38 escorts could maintain formation throughout marathon missions. The air superiority that enabled D-Day and subsequent ground operations in Europe was established partly by P-38s. They could contest airspace at any altitude without mechanical limitations. The island-hopping campaign across the Pacific proceeded faster than planned. P-38s neutralized Japanese air power that might otherwise have delayed advances significantly. Each of these outcomes traces partial lineage to one engineer's refusal to accept impossible as a final answer. He saw a problem others had declared unsolvable, recognized it as a physics challenge rather than an aviation mystery, applied industrial engineering principles to an aerospace application, created a solution so elegant that its descendants still operate in modern aircraft 7 decades later. The human element transcends technical achievement completely. Those 290 pilots who survived because reliable engines didn't fail them at critical moments returned home. To families who had waited anxiously. To careers that contributed to peacetime prosperity. To lives they would have been denied. They had children, second-generation beneficiaries of brilliant engineering. Those children had their own children. creating ripples of life that extend through multiple generations, all descended from men who lived because liquid fuel flowed smoothly at 30,000 feet. The modification also demonstrated truths about innovation that remain relevant today. Complex problems don't always require complex solutions. They require correct solutions applied at the right intervention point. Bureaucratic processes can accelerate dramatically when urgency meets leadership. Leadership willing to accept calculated risks. Individual expertise matters profoundly. Organizations must create environments where good ideas can emerge and flourish rapidly. The engineer embodied the quiet competence that won World War II as surely as battlefield heroics. He never fired a shot in anger, never flew combat missions, never made newspaper headlines. He sat at a drafting table in Burbank, California, studying pressure data until he recognized a pattern, then designed a valve that saved hundreds of lives and changed strategic outcomes across 2 theaters of global conflict. His story reminds us that wars are won not just by those who fight, but by those who think. Engineers, scientists, technicians, and innovators whose contributions enable warriors to prevail. The P-38 pilots who dominated high-altitude combat from late 1943 onward were heroes, certainly. But their heroism was made possible by an engineer who refused to believe a problem was unsolvable. Just because everyone said it was, didn't make it true. The final legacy rests in museums where restored P-38s stand, in engineering textbooks where the modification appears as a case study, in the descendants of pilots who survived to come home, in the institutional memory of organizations that learned how quickly good engineering can change everything when supported properly and deployed aggressively. One engineer, one insight. 76 days from concept to combat validation. Nearly 3,000 aircraft modified. Hundreds of lives saved. Strategic outcomes altered permanently. A principle proven that echoes through generations. Impossible is often just a failure of imagination, waiting for someone smart enough and stubborn enough to prove otherwise. The fork-tailed devil earned its fearsome reputation not through intimidating appearance, not through overwhelming firepower, but through reliable excellence at altitude. The kind of unglamorous superiority that wins wars. That reliability existed because one engineer looked at data everyone else had seen, recognized what everyone else had missed. Sometimes victory belongs not to the strongest or the bravest, but to the smartest person in the quietest room, working the longest hours, refusing to accept that impossible means anything more than not solved yet. That was his gift to the war effort, to the pilots who flew home, to the families who welcomed them back, to the future generations who exist because reliable engines brought fathers home from war. The impossible, it turned out, just needed an engineer who understood pressure dynamics. Someone who refused to quit until the numbers made sense. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.